Our algorithm is named minimum degree of saturation. It is based on the degree of saturation algorithm. The steps that MDSat takes are as follows. First, generate degree ordering of V. Second, select a vertex of minimal degree and color it with the first color. Third, consider a vertex with the lowest degree of saturation. To break ties, consider the vertex with the lowest degree. Further ties are broken randomly. Fourth, loop through the color classes created so far and color the selected vertex with the first suitable color. And finally, unless all vertices are colored, return to step 3.
We used sample datasets to test the performance of our algorithm. These were sourced from the Center for Discrete Mathematics and Theoretical Computer Science, or popularly known as DMAX, and distributed by the Turing CSS website. These datasets are graph representations of register allocation problems and are in the form of text files. We chose 10 of these text files.
The content of each file looks like this. The first line indicates the file name, and on the ninth line we see information about the graph. P-edge 496-11654. That means the graph will have 496 vertices and 11,654 edges. The succeeding line shows the information about vertex adjacency. For example, E12 means an undirected, unweighted edge exists from vertex 1 to 2.
We have implemented a Java program to read each one of these files and to convert them to a Java graph object. This is how the Java program works. So first, it reads the links from one text file that contains one dataset. Then the program goes to the link where the benchmark instances are hosted. Third, the program reads the web page and then scrapes the text data to a text file. Then the text files are converted into graph objects, and then the benchmark algorithm starts.
The benchmark algorithm DSAT will be benchmarked against first fit and DSAT. The program will take input the graph objects, then for each one of the graph coloring algorithms MDSAT, first fit, and DSAT will solve each of the files 1,000 times. At the end of the 1,000 runs, the modal value of the approximation and the average runtime of these algorithms will be saved. The results will tell how efficient in terms of time and in terms of approximation MDSAT is. To make the task easier, the program automatically tabulates the data into an Excel file.
Now we proceed to the results. MDSAT and first fit were compared against the time performance of DSAT. This was done because theoretically, DSAT is the best algorithm for register allocation problems out of the three. The most important part of the table are the columns labeled with time difference with DSAT and color difference with DSAT. Focusing on the bottommost part, the mean differences, we can gather two insights. First, MDSAT runs slower than DSAT. The positive time difference of MDSAT implies that DSAT ran faster in solving all of the register allocation problems. The data says that in average, MDSAT runs 5.8 milliseconds slower than DSAT. Second is that first fit runs faster than MDSAT and DSAT. The positive time difference for first fit implies that it ran faster than DSAT and MDSAT in solving all of the register allocation problems. The data says that in average, first fit runs 10.78 milliseconds faster than DSAT.
Now we show the second set of results. Focusing on the bottommost part, which is the mean differences, we can gather two insights. First, MDSAT gives better approximations than DSAT. The negative color difference of MDSAT implies that DSAT overestimates the chromatic number or coloration in solving all of the register allocation problems. The data says that in average, MDSAT gives 1.5 less colors than DSAT, which is surprisingly good. Second, MDSAT gives better approximations than first fit. The positive color difference of first fit implies that it gave the worst approximations in all the register allocation problems for all the sample graphs when compared to both MDSAT and DSAT. We can see that first fit consistently gave positive values, which means that first fit gave overestimates in approximation all the time. As discussed in the previous figure, though first fit runs faster than MDSAT and DSAT, it gave overestimations of color approximations. Hence, first fit is fast, but at the cost of solving the closest optimal solution. From the data, we conclude that MDSAT is faster and gives better approximations when compared to DSAT.
The vertical axis and the horizontal axis shows the color or time difference and the number of edges of the sample given its density. The figure shows what happens to the differences as the graphs become denser. We can say that the density does not largely affect the color approximations of MDSAT because a trend does not exist. Rather, the hotspots can be found on graphs with greater number of edges. Therefore, we say that as the number of edges increases, the tendency is MDSAT overestimates, and when it overestimates, its runtime worsens.
In sum, the results show that MDSAT gives better approximations than both DSAT and first fit. However, it is the slowest algorithm of the three. Throughout the test, it is safe to say that our proposed algorithm for the register allocation problem, MDSAT, is feasible for the domain. Though through this study it was proven with a small number of test cases that minimum degree of saturation is better than first fit and degree of saturation algorithms, it remains to be a hypothesis to be tested. To conclude such theory, the researchers recommend the following to further the study. First, to benchmark MDSAT on bipartite, cycle and wheel graphs on which DSAT always gives an exact solution. Second, benchmark the algorithms against datasets where the chromatic number is known to give a more accurate assessment on the performance. Third is to increase the size of the datasets to make the results more accurate. Fourth, to increase the variation of graphs to benchmark against to determine the strengths and weaknesses of MDSAT. And finally, to include more algorithms to benchmark to better assess the performance of MDSAT.